Okay, I'm going to try to get through as many of the together problems as I can in this video, and if I need to make a next one, I will. Alright, the first one that I told you though I'd go over is 61b. Okay, now 61b, what we're looking for is we're looking for two things. We're looking for the pH at the halfway point as well as at the equivalence point. Okay, so we're looking for our half as well as at our equivalence point. Now remember, whenever we have a half titration, okay, as soon as you're halfway there, your pH is going to be equal to your pKa value. Okay, now for part B, what we were titrating is we have 100 milliliters of 0.10 molar. Okay, and this is our base, and this is the Kb value. Now we know it's going to act as a base because it can accept the hydrogen ion on that last with the nitrogen, the ammonium. The nitrogen on the end. It's got one more spot for a hydrogen ion where it can accept it, and its Kb value is 5.6 times 10 to the negative fourth. We're titrating it with 0.20 molar nitric acid, which is a strong acid. Okay, so it means we don't have a Ka value. Makes the math easier. So first off, for the half equivalence point, we have to find the Ka value, and we do that by taking Kw, which is 1.0 times 10 to the negative 14th, we're going to divide our Kb value, which as we found over there is 5.6 times 10 to the negative 4th, sorry, as they told us over there. Okay, so then our Ka is going to would be equal to 1.8 times 10 to the negative 11th. Remember, pH is equal to pKa, so what I have to do in order to find pKa is take the negative log of 1.8 times 10 to the negative 11th, and that's going to give me a pH value of 10.74. Okay, so boom, there we go, which makes sense because we're starting with a basic solution, we're titrating it with an acid, and we're only halfway there, so we're at 10.74. Now, at the equivalence point, if you remember what's going to happen here, we have to figure out how many moles of the base we originally have and figure out how many moles of acid that we're going to need to add in. So let me do this over here, see if I've got enough room. So at the equivalence point, again, the moles of acid, actually we're doing millimoles. Millimoles of acid are simply equal to the millimoles of the base, okay, that were presented. And so in order to figure this out, if we look at the 100 mils, now you will need to show me evidence that you've watched these, so you probably should be jotting some of this down as we go through these problems. So 100.0 mils times 0.10 moles per milliliter. Okay, we can use that so that we originally had 10 millimoles of our base to start with. So C2H5 and H2. So if I know I have 10 millimoles, then I had to add 10 millimoles of the nitric acid as well. But what I got to figure out is the volume that I would have had for that. So at the equivalence point for my nitric acid, okay, I would have 10 millimoles. Okay, so 10 millimoles of hydrochloric acid over the new total volume, which we had 100 mils of this. Now, since this is twice as concentrated, okay, it's twice as concentrated here, it's gonna end up being 50 mils. Now, the way that I can calculate that, 50 mils, half as much. So if I have 10 millimoles, my concentration is kind of a backwards 0.20, backwards molarity. So that means that I needed 50 mils of the hydrochloric acid. Okay, or you can look at that. Well, this one's twice as concentrated. It's a 1-to-1, so I'm going to need half as much to titrate it. Okay, at this point we should hopefully be able to make some of those connections because that's somewhat simple stoichiometry at this point. All right, now if I come back over here So now I know I had my 50 mils of hydrochloric acid, and what I'm looking for is I have to figure out the pH. Now at the equivalence point, it's not the original weak base, and it's not the original strong, or not the strong acid that are going to influence it, because there isn't any left of either of those. What is going to influence it is the conjugate acid of this material, okay? So remember, if I come back over here, try to get my mouse, there we go. All right, so the chemistry that's going to happen is that the conjugate acid is just the product of when we've added that hydrogen ion, and it's going to then dissociate somewhat, and that's all that's left to influence our pH. So C2H5 and H2. Now we already found our Ka value up here, so we're good because we already found our Ka using our Kb. And what we have to figure out is what the concentration was. Now we still have 10 millimoles, right? So we've got 10 millimoles, and in that 10 millimoles it's diluted by or into 150 milliliters, okay, which is actually going to give us, I'll drop down here just a second, okay, give us some more space. So that actually, the math-wise, comes out to be 0.067 molar. Okay, we have 0 hydrogen, we have 0, and now it's a simple, straightforward Ka problem. So my change minus x plus x plus x, 0.067 minus x, x, and x. So I set all that equal for Ka. Remember, for a Ka expression, this is just a reminder, the thing that you know you always have a Ka expression is that if one of your products is hydrogen. Okay, now in this case, I'm writing the whole thing out just to reemphasize it, but you know, there's our hydrogen ion. Kb is the opposite. You have to have hydroxide up here. Okay, so that's one of the ways you know whether you have to use Ka or Kb is what you're generating. Now, like I said, we found our Ka value, 1.8 times 10 to the negative 11th. We set that equal to x squared over 0.67 minus x. The assumptions work out, so our x comes out to be 1.1 times 10 to the negative 6th. We're trying to find pH, so we're going to plug that into our pH equation, take the negative log of 1.1 times 10 to the negative 6th. So our pH is going to end up being, should be close to around 6 because of the math here, and it does. It comes out to be 5.96, which also makes sense because when you have a titration of a weak acid, or sorry, a weak base and a strong acid, the pH value at the equivalence point is slightly lower than 7 because the only thing left to influence it is that weak acid. Okay? Alright, so that's 61B. Now 61C, we're going to have 100 mils of 0.5 molar hydrochloric titrated with 0.25 molar sodium hydroxide. Okay, so this is when we've got a strong acid and a strong base, which means no Ka and Kb values, which makes it the math easy. Now we just got to figure out what we had reacted with. Now for 100 mils of 0.5 molar, okay, so 0.5 millimoles per milliliter. It means that originally we're going to have 50 millimoles of hydrogen ion. Okay, now none of the, just as a reminder here, none of the pKa is equal to pH stuff counts because there's no Ka values. So for our half titration, we literally just have to figure out how much half of it was to be neutralized. So at our half titration, if we are starting with 50 millimoles of the hydrogen ion, it means that only 25 millimoles of hydroxide were going to be present. Okay, so all I then have to figure out for these is that I have 25 millimoles of hydrogen ion left. All the hydroxide is going to be neutralized, so there's nothing left there. And then all I have to do is take that new amount, divide it over the new volume, okay? And if I had 100 mils of 0.5 molar, if I come back up here for 1 second, in order to figure out the volume that I would have added, okay, and again, for those of you who are good at math, you know, it's not hideous. 1 milliliter 20.25 molar millimoles. That means that I was going to have to add 100 milliliters to neutralize it, okay, or half neutralize it, which again makes sense if you take a step back. This is half as concentrated, so I'm going to need the same amount to half titrate it. I would need 200 mils to titrate it completely. All right, so for my new concentration, I take 25 millimoles, I divide it by 200 milliliters. That gives me a new hydrogen ion concentration of 0.13 molar. I plug that right into my pH equation, so I take the negative log of 0.13, and that gets me a pH value of 0.89. Okay, and right at the equivalence point, this is a strong acid. Okay, so since we're dealing with strong acid, strong base problem, our pH at the half titration was 0.89. Okay, and then since it's a strong base and a strong acid problem, at the true equivalence point, the pH is truly neutral, 7.00, because there's nothing left to influence the pH at that time. Okay, the next one that we're going to talk about is 63. And I think I'm going to stop here and make a second video for 63 and 65, and then we'll just keep working through it.